Please stand by. Good day, ladies and gentlemen, and welcome to the Hubbell Power Systems Chance Cutout Experience Conference Call. Please note today's conference is being recorded. I would now turn the conference over to Mr. Charles Worthington. Please go ahead, sir.
All right, I want to thank everybody for joining this part 2 of our Mission Critical Protection presentation on cutouts. Today will be the experience presentation. For those of you who joined the first one, we're going to do a little bit of review at the beginning, cover some of the Chance history, and then we're going to get a little more technical and discuss some of the aspects of the polymer and porcelain cutouts in a little more detail than we did last time. For our summary, as I mentioned, we're going to go through, we'll talk briefly about the history of Hubbell and Chance, and then we'll move through the porcelain cutout manufacturing, and then break into polymer cutouts and do the synthetic liner, the ESP rubber material that we use from Ohio brass for our polymer cutout, the pultruded core rod, crimping, molding, and finish it up with environmental testing. In the late 1800s, Hubbell was established. They released products like the pull socket light switch, which is still in use today. I'm sure most people are familiar with this product. This is really a baseline for Hubbell. They were always trying to innovate in the electrical and power areas. In the early 1900s, Chance was founded, and shortly thereafter, or shortly before, Hubbell was also incorporated, and then they pursued and purchased Chance in the early 90s. Chance originally released the porcelain cutout Type C design that you see today in the late 70s. This design was innovative because it changed the cutouts from a dual vent design, which I'm sure some of you have seen online still today, to a single vent design, which is what most manufacturers are offering. And we also incorporated the use of interchangeable fuse holders. Originally, when it was released, the Type C Chance cutout allowed S&C fuse holders to be used in the mounting assembly. After the acquisition of Chance by Hubbell, shortly moved production down to Juarez, Mexico. In the early 2000s, we replaced the synthetic fuse tube liner from the bone fiber liner. And since 2003, with the release of the 15 kV, and 2005 for the release of the 27 kV, we've been split production about half and half between porcelain and polymer cutouts. In 2011, Hubbell opened a production facility in Wuhu, China, and now we maintain production in both the Juarez, Mexico plant and the China plant. As I said before, in the late 70s, Chance took an engineering design to make fuse holders interchangeable between multiple manufacturers. The first fuse holder, of course, was the S&C fuse holder. Being one of the leading competitors, that was what Chance sought out. Today, Chance cutouts accommodate the ABB style fuse holders as well as the S&C, and those are, of course, interchangeable between the porcelain and polymer mounting units. All of the designs are the same length with the same voltage class rating. So 15 kV units are all the same length, 27 kV and then 36 kV are, of course, all the same length. So to briefly cover our porcelain cutout manufacturing, one of the critical things Chance has done over the years is to implement a proof load for all porcelain on incoming inspection. You'll see in the bottom photo here, this is the fired foot of the insulator. You will see a T stamped across the bottom in 3 different positions. The porcelain is all proof loaded at 0, 90, and 180 degrees. This ensures there's no major flaws in the design or in the manufacture of the porcelain. There's no major cracks that are going to affect the overall strength of the unit. And again, this is done 100% on all porcelain before it is received in the plant. One of the requirements for pioneering the interchangeability was to maintain the length of the polymer or the porcelain units to allow for similar testing between both the S&C fuse holders in the Chance unit as well as the Chance fuse holders. So to do that, manufacturing made a decision to pot the completed assemblies at the same time. So you'll see here there is no sulfur cement, which is the cement we use to fix the assemblies inside of the porcelain. You'll see here in this picture there's no cement inside those cavities yet. We assemble all of our components prior to seating that inside the porcelain. That allows us to maintain that length and allows us to accommodate interchangeability between manufacturers when you have varying tolerances. Here is in these photos you will see the porcelain potting fixtures. In the rightmost photo you will see the sulfur cement. Typically what you're going to see is a black sulfur cement. Sulfur cement is of course susceptible to UV and water ingress, so a synthetic, a polyurethane paint is used on the top of the sulfur cement to protect it from UV light and water. For those who joined the first presentation, we covered synthetic liners and bone fiber pretty in depth, so here we will cover it again. We will add a little bit of information for those who did join the first time. You will get a little bit more in-depth into the design and testing of the synthetic liners. One of the main issues bone fiber has is the susceptibility of it to absorb water. So as a unit, as a fuse holder stays out in the field, humidity, certainly in the southern United States where the humidity is very high, and all across the country, as you get rain, the bone fiber will tend to swell. On a 100 amp style fuse holder, the larger lengths, the 80 amps, 65, 80, and 100 amp lengths, are very close in outer diameter to that of the inner diameter of the bone fiber liner. So as they swell, they can tend to grip a fuse link. Once the fuse link operates, if the liner is gripping the fuse link, it will of course cause the fuse holder to fail, to drop out. In that event, you're not going to interrupt a fault had there been a higher current fault, and you can draw an arc. Or the fuse holder could weld into the cutout and remain in place, eventually tracking across the fuse holder. In the early 90s, Chance started development on a synthetic liner using some of their chemical engineers. Having a test lab in Centralia, Missouri allowed Chance to test quite frequently on the synthetic liners. So even though we started in the early 90s, the liner was not even released until the early 2000s, 2001, as noted on the timeline. So as you can imagine, we went through quite a number of interruptions. And for those familiar with the standards, there are 5 test series for fault current interruption. So in each of those series, you're going to range in fault current from a few hundred amps up to 10 or 16,000 amps. So each of those series has to be tested to qualify the liner. As you can imagine, it took a number of years, 7 to 8 years, to fully develop a synthetic liner that would work at all fault currents and to get the chemical composition of the liner just right. One of the variations between bone fiber and synthetic liner is that as it absorbs water, that water plays a role in not only the ablation of the liner, but in the arc quenching ability during fault interruption. So as the arc draws through the fuse holder, you will destroy some of the liner inside, and depending on the amount of water inside the liner, this will cause variation in the interruption process. So having the synthetic liner with a very low water absorption property allows you to eliminate much of that variance during interruption. Again, the test lab allowed thousands of tests to be done on the synthetic liner and developed the proper chemical composition to maintain consistent interruption properties. And still to this day, all of our fuse tubes are produced in the plastics lab, or the plastics manufacturing facility in Centralia, Missouri. We'll break into polymer cutouts now. I think everyone has probably seen this cross-section before. This is a standard photo we have in our catalog. There are four major components to the polymer insulator design. You have your core rod, which runs down the center. It's a pultruded fiberglass rod. This is what's going to give you your dielectric properties and maintain strength of the insulator. You have stainless steel fittings, of course, to attach hardware. You have a chemically bonded interface between the polymer and the rod, as well as the stainless steel fittings. And then you have your ESP, or your rubber. Ohio Brass, a sister company, they were actually acquired by Hubbell many, many years before Hubbell acquired Chance. And they had a long, successful history of molding EPDM. In the 70s, they developed the ESP formulation, and it was eventually released. And this is primarily the formulation that they use for their PDI insulators. So when development began for the polymer cutout in the late 90s, Ohio Brass was, of course, incorporated, and ESP was chosen as the material to use for the polymer cutout as well. Having so much experience molding over the years, it was a fairly simple transition from a PDI to a polymer cutout. The way Ohio Brass qualifies, you'll see some of these photos here. The initial polymer design analysis done by Ohio Brass involves tracking tests, ultraviolet, oxidative stability, corona cutting, and salt fog. Essentially, these are all environmental tests intended to check the durability of the polymer to withstand the UV light, as well as contamination buildup on the surface, and all the while enduring electrical stresses. So some of these tests here are what was done initially on development of the ESP and is still done routinely today. The pultruded glass rod is probably one of the most critical, other than the ESP formulation, to the strength and dielectric properties of an insulator. You'll see here in the bottom left-hand photo, this is a dye penetration test. Although the rubber is already molded over the unit, this is a standard test performed during production on the rod as well. Various dyes can be used to generate this. But what is going on here is you're checking the rod for complete fiber wet out. Of course, if you have holes or fibers in your rod that do not get wet out by resin, that of course creates a path for electrical current to travel. So the dye penetration essentially checks for holes, and as you can see here in the photo, after you mold, it of course checks for cracking across the rod that can occur due to the thermal shock experience during the molding process, and it also checks for cracking due to the crimping process, which we will look at in a second. The right-hand photo at the bottom shows it's essentially an impulse on the rod. This is going to test the dielectric strength of the rod. Again, this is a routine test done. Chance has a long history of rod pultrusion. We maintain lines in Aiken, South Carolina as well with Ohio Brass. Much experience and testing has gone into the development of this rod, and its use in polymer cutouts was an easy transition as well as the rubber was. Another critical component is the crimping and fittings. Here you will see a PDI insulator. The difference between the cutout crimping and the PDI crimping is, of course, the cutout fittings are overmolded. So the crimp is very important. A crack in the rod prior to molding could cause a further propagation during molding with increased thermal stresses. So over the years, Ohio Brass has developed a 360-degree crimp process. This keeps the load around the entire rod even throughout the process and eliminates the possibility of cracking occurring. This is the same process that we transferred over to the polymer cutouts. Of course, it is done before molding, so you will not see an insulator on the press. But here you can see a picture of the press that is implemented. It's a little bit difficult to see the full press, but essentially the mold is the same as the PDI design, and then you will see the impression left after the crimping process occurs. This is the center pin in the right-hand photo of a polymer cutout. If you look closely on the left-hand side of it, you can see another indentation. There are, of course, 6 indentations around the fittings. This allows, again, elimination of rod cracking, and it also gives the fittings a very high pull-off strength that, of course, needs to be withstood during a Series 1 interruption, which is a higher current fault interruption. Forces and loads can be very high on the end fittings, of course, during this test, and so a good crimp is required to maintain integrity of the unit following an interruption. Here you will see a picture of the molds used for the polymer cutout. Prior to going into molding, one of the other critical components, which we mentioned earlier, is the interface. So prior to molding, all of the rod assemblies, which is what the pultruded rod and the end fittings are known as when they're connected together, are coated with an adhesive to allow the polymer to stick. Throughout the years, we've made significant improvements in the application of the adhesive as well as the adhesive itself. Being different materials, the core rod and the stainless steel fittings, it's difficult to maintain your rubber interface on both materials. The critical test for this is going to, of course, be water penetration for those who are familiar. Water penetration subjects the insulators following molding to a 100-hour boil in salt water, and then it, of course, stresses it with a power frequency test, which is a dielectric withstand test for the insulator, as well as a steep front impulse, and followed up with a temperature rise. So during molding, of course, if you have a part of your rod assembly which is not coated with adhesive, you can have non-bonds, and those non-bonds are going to lead to water ingress or air ingress inside of the insulator, and those flaws will, of course, be called out during steep front impulse or during temperature rise. Any air between the polymer and the rod is, of course, going to cause some temperature rise when electricity is applied to it. Again, you will see a completed insulator here in the leftmost picture, followed by an inspection of the unit. Again, we'll go back to bonding for a second. As I mentioned, the core rod and the stainless steel fittings, being different material, of course, require a little bit different treatment during adhesive application. Initial prototyping, we used galvanized steel fittings for the polymer cutout. This, of course, led to issues during molding. As you can see in the rightmost photo, the rubber is not attached to the unit whatsoever after a peel test is performed. The peel test is, of course, a 100-hour boil again, and then the rubber is peeled from the unit. During this 100-hour boil, if there is any non-bond issues, the rubber will tend to slip easily off the surface of the rod or the stainless steel or galvanized steel fittings. So originally, when Chance was developing the polymer cutout, the galvanized steel fittings performed a little bit more poorly than the stainless steel fittings, and so we made a switch to those. So to sum up for today, as I mentioned, Chance has had a long history of interchangeability. We maintain a very tight control over the potting process for porcelain cutouts to accommodate the S&C and the ABV units. And Ohio Brass's experience in the polymer cutout was, in crimping and in the rubber, was critical to the development of the polymer cutout. It allowed a quick design and quick release. And we maintain all of those components. We maintain the fiberglass rod protrusion as well as the rubber material. We retain all that knowledge within the company, so it greatly assists during improvements. Testing is always very consistent. And of course, the crimping was one of the critical aspects of the polymer cutout. The full 360-degree crimp eliminated any issues with rod cracking. It allows the cutout to maintain its integrity through mechanical stresses. Loading, of course, cyclic loading from opening and closing a unit is, of course, going to put wear on the insulator as well. And those improvements have also allowed us to produce a unit that consistently passes testing. At this time, our 27 kV unit has passed all of the CSA C31009 polymer cutout standards design tests. This is the first standard that has specifically addressed the polymer cutout design. Currently, most standards, including IEEE, only address porcelain-related insulator tests. The CSA standard has come in and implemented some PDI tests as well as some IEC tests to apply environmental loads and accelerated weathering to the polymer cutout to test the insulator itself. Of course, all of the other tests mentioned in CSA are transitioned from the ANSI standard. At this time, if anyone has had any questions throughout the presentation, I would ask that you submit them using your live meeting software. In the top right-hand corner, on the toolbar, you will see a Q&A section. If anyone has any questions, we would gladly take those, and we will answer those at this time. Okay, one question we have is regarding the crimping process. A longitudinal crimp, as you'll see in the, we'll scroll back to the photo here. You can see it in this photo. As you note in this region here, the crimp is a longitudinal crimp down the axis of the core rod. This aids in the stability of the fitting to the rod. A horizontal crimp can induce cracking. The surface area is lower, or the surface area is not lower, but the crimp is perpendicular to the axis of the fibers. So this can induce cracking by putting a point load on the fibers themselves. Another question is, has the 15 kV unit passed the CSA standard at this time? There are some stipulations in the CSA standard that require us to retest. Technically, the 15 kV unit, we have no doubt, will pass all of the tests, but due to some of these stipulations that are somewhat different, at this time our 15 kV unit does need to be retested. If anyone has any further questions on that, they could, of course, address us individually, and we will be glad to provide any test reports and go into further detail on those individual tests that we need to perform again. All right, at this time, I have not received any additional questions. I want to thank everybody for joining the presentation today. I hope it was as informative as the first presentation. The last presentation is going to run a little bit longer than this one. It's going to be Part 3, Quality, on August 28th at 2 p.m. If everyone would like to register for that, you can register at the same link. It should be switched over at this point. And we look forward to seeing everybody on August 28th. If anyone has any further questions after this presentation, feel free to contact us. And we have done a recording of this session and the first session, and we'll make it available for those who would like to review the presentation, or for those who missed something or would like to share it with some colleagues. As soon as we get that uploaded to the website, we will, of course, send out an alert. Thank everybody for joining today. I hope to see you next time.
Thank you. And again, ladies and gentlemen, that does conclude our conference for today. We thank you for your participation. You may now disconnect.